Hi everyone. In this video I will be talking about regression diagnostics with a focus on influence analysis using SPSS. And the reason why this topic is important is that when you are performing a regression analysis, you do not want to have a small subset of cases that are dominating your regression solution. So it's only through identification of potentially problematic cases that you can then develop a strategy for how to deal with the issue. Now this video presentation is pivoting off of a PowerPoint presentation that I put together on this topic, and you can download a copy of the PowerPoint by following the link that's provided underneath the video description. And in the PowerPoint there are three regression examples. The first two involve simple regression and the third one involves a multiple regression, and that's the example that we are going to be referring to throughout this video demonstration. I also want to mention that under the video description you will find links to the SPSS data files that were utilized in the development of the PowerPoint, and the third data file is the one that we are using in this video. So before we open up SPSS, let me just talk a little bit about the indices that we will be referencing throughout this video. So the indices that I'm going to be talking about include Cook's D, Standardized DF fit or DF fits, Standardized DF beta, also referred to as DF betas, Studentized residuals, and then the squared Mahalanobis distance. Now Cook's D, DF fits, and DF betas can all be considered influence diagnostics in a proper sense. So with Cook's D and Standardized DF fit or DF fits, what we're looking at with those indices is the degree to which a case is exerting high influence on an overall model. Whereas the Standardized DF beta or DF betas can be used to identify those cases that have high influence on individual parameters. The Studentized residuals and squared Mahalanobis distance, these are not influence statistics per se, but rather they capture aspects of your data that bear on the likelihood of a case being influential. So if we can define influence as a product of discrepancy or distance and leverage, then we can utilize the Studentized residual and the squared Mahalanobis distance as a way of identifying cases that have potential influence. So in other words, these cases do not measure these measures do not capture influence directly, but rather they capture potential influence. Now you will notice in this table that I've included absolute thresholds and size adjusted thresholds. So absolute thresholds are those that are kind of rules of thumb, if you will, that are commonly referenced in the literature. Then we have size adjusted thresholds, particularly for Cook's D, DF fits, and DF betas, and these are adjusted for your sample size. And just so you know, I've included in the PowerPoint these indices along with references to where I located them. So the size adjusted Cook's D can be computed as 4 divided by n minus k minus 1, where n is the sample size, k is the number of predictors, and obviously we're subtracting 1 as well. Then with respect to DF fits, the size adjusted threshold can be computed as 2 times the square root of k plus 1 over n, where k is again the number of predictors and n is your sample size. For the Standardized DF beta or DF betas, we can divide we can divide 2 by the square root of n. So if you open up the PowerPoint and go to example 3, these would be the size adjusted cutoffs associated with Cook's D, DF fits, and DF betas. So let's go ahead and open up SPSS and generate our diagnostics. So here we have our data set opened up, and the dependent variable in our regression model is this achievement variable, and our independent variables or predictors are interest and mastery. And you'll notice that we only have 100 cases in our data set. So to run our analysis and to generate our diagnostic measures, what we'll do is go to Analyze, Regression, we'll go down to Linear, and we'll move achievement to the dependent variable box and then interest and mastery to the independent variable box. We'll click on save, and I'm going to select Studentized and Standardized DF Betas, Standardized DF Fit, Mahalanobis, and Cook's right here. Obviously there are other indices that we could select, but we're not going to do that in this video. So I'm going to click on continue right here and then on OK, and you'll see that we get our basic regression output. There's our model summary, our ANOVA summary table, our regression coefficients, and then you have this table containing residual statistics, and included in this we have, it says minimum and maximum values. This is kind of a nice way of or a nice tool for sort of getting a bird's eye view of whether there might be some issues with some of those diagnostic measures. So you can see right here that with the studentized residuals, they range between a negative 2.746 to 3.062. So you can see this one would exceed that absolute cutoff that we were referring to with respect to the studentized residuals. You'll see that there's the minimum and maximum value for Mahalanobis distance. There's no absolute cutoff, but I'll show you how you can look at we can use that to evaluate cases for being high leverage in a bit. Then we have Cook's D, and we've got 0 as a minimum, and then 0.804 as a maximum, and that maximum exceeds our size adjusted cutoff. Now when we go into the data set, we can look at each of our indices. So we have case-wise indices for the studentized residuals, Mahalanobis distance, or basically the squared Mahalanobis distance, Cook's D, the DF fits right there, and then we have our DF betas, which this is for the intercept, this is for the slope associated with the interest predictor, and then the slope associated with the mastery predictor. And one of the things that I want to do too early on is to create an index variable. So at this point I'm going to go to transform, compute variable, and I'm going to type in ID or index or whatever right there, and then under numeric expression I'm going to type in a $sign followed by case NUM and click on OK. And so basically we're going to generate case number variable, which is going to serve as an index associated with each of the cases. And this can be particularly handy when we start, if we do any kind of sorting on these variables and then trying to identify which case is perhaps higher in influence. So let's start off looking at Cook's D, and these are the Cook's D values in our data set. So this is associated with each individual case, and a quick and easy way to look for potential influential cases would just be to sort on that variable, and then we can just kind of easily scroll down and look to see where the largest values are. And so you can see again with our ID variable over here, these were the original case IDs, and so if we look at this Cook's D column right here, you can see that we have no cases that exceed the absolute threshold of 1, but we also have these cases right here that would exceed the size adjusted threshold. Nevertheless, we also want to pay attention to those situations where we have considerable gaps in our Cook's D value, and so you can see that case number 51 has the second largest Cook's D value, and then followed by case number 76. You can see that there's a substantial gap between those cases with respect to Cook's D. So this is kind of a tell that case number 76, or ID, the case with the identifier of 76, may be a case to be concerned with. Now another option is to try to visualize the Cook's D values and basically creating an index plot. So if we go to Graphs, Legacy Dialogs, and go to Bar, click on Simple and then Define, what I'll do is I'm going to move the ID variable over to the category axis, and then I'm going to move Cook's D or Cook's distance over here I need to click on this first and then move Cook's D over and then on OK, and you'll see that now we have an index plot, and I can kind of stretch this out a little bit right here, and you can see that case number 76 is obviously demonstrating a much greater influence relative to the other cases in the data set. Okay, so now let's take a look at our DF fits. So in this case, I'm going to use my sort cases function right here. I'm going to remove Cook's D, and I'll put DF fits in here like so, and click on OK. And now when we go to our data set, you can see right here that the lowest value with respect to the DF fits is minus 1.6. So certainly that's not the absolute value of this is not exceeding the absolute threshold or cutoff of 2, and when we scroll down you can see that the largest value, positive value, is also not exceeding that cutoff. But nevertheless, we do have cases that are exceeding the size adjusted cutoff of 0.346. So basically these are values on the positive end that are exceeding that size adjusted cutoff, and then when we scroll up you can see that we have basically just this case right here that's doing it, and that actually this is the largest DF fits, and that is associated with, you guessed it, case number 76. So now let's do a quick index plot just to take a look at this. So we'll go back to bar graph right here, go under simple, and we'll move Cook's D out, and we'll put DF fit in, or DF fits in, click on OK, and so there you go. You can see that you have that one bar that is really reaching, that's really pronounced, and again that is obviously our case number 76. Now obviously we can follow the same set of procedures when we're looking at the DF betas, so for the intercept, for the slope for our interest predictor, and the slope for the mastery predictors. And I'm going to save you, in the interest of time, I'm not going to go through each of those, but I'll refer you back to example 3 in the PowerPoint. But I will say as a heads up, the case number 76 appeared to have the largest DF betas for the intercept and also for the slope associated with the interest predictor, but it turned out that case number 51, or ID 51, had the largest DF betas for the mastery predictor variable. So next, let's go ahead and look for residual outliers, and we can do this using the Studentized residuals right here. So again, I'm just going to do a quick sort on these, and we'll go in here to Studentized residuals, click on sort by again, and now we will see in this case that actually none of the Studentized residuals except for this residual right here are greater than 3. So that residual is actually associated with case number 51. The next largest studentized residual though is associated with case number 76, which is this one right here. Again, if we wanted to generate an index plot, we can easily do so just by going back into our bar graphs function. So if I move this out, I can move studentized residual in, and just so that we can take a quick look at it, you can see right here that there are two bars that seem to be more pronounced. So obviously one bar, this is for case number 76, this was one of the larger bars, but it didn't meet the threshold for being an outlier, whereas in this case right here, this is case number 51 that we had talked about previously. Alright, so now let's transition and talk about our index of leverage, which we're using the Mahalanobis distance, or basically it's the squared Mahalanobis distance in SPSS. And for this one, what we'll do is we'll go ahead and sort on this. It's always nice to take a quick look at this, so we'll sort on it and look at the size of the Mahalanobis distances, and you can see that obviously here's our lowest value, and then here's our highest value, and you can see basically that highest value is associated with our case number 76. and you can see that there's a pretty substantial gap in terms of the Mahalanobis distances between case number 74 and 76. So the 74 had the next largest value. So we can use the index plot as one way of sort of visualizing that that gap. Another thing that we can do is we can test the cases to identify potential multivariate outliers. And so when I say multivariate outliers, I mean outliers with respect to the predictor variables within the model. And so theoretically speaking, a multivariate outlier would be a case that would be exhibiting more extreme values on the predictor variables. So if we find statistical significance for a test of that sort, then that would be an indication that we have a case that may be of high leverage. So to do that, we can use a procedure that's outlined in several stat books that I've read. And what we'll do is we'll go under Transform, Compute Variable. We'll reset this, and I'm going to generate a variable called p-value. And under numeric expression, I'll type in 1 minus. And you can go under here, if you don't want to type it, you can click on CDF and non-central CDF. That's for cumulative distribution function, and click on CDF for chi-square. And if you double click, it'll show up under the numeric expression. And for the first question mark, what we'll do is we'll move Mahalanobis distance over into that position, and then for the second question mark, we include the number of predictor variables in our regression model, and that happens to be 2. So now we'll click on OK, and so a new variable has been created in our data set called p-value right here. And because we've actually already sorted on the Mahalanobis distances, or the squared Mahalanobis distances, we can just kind of scroll down, and one threshold that Tabachnik and Fidel reference was a p-value of 0.001 or less as an indication of a potential outlier. So we can scroll down and look for that, and I'll just really quickly go under variable view right here, and I'm just going to go ahead and increase the number of decimal places here to 4. And so you can see that the only case that has a p-value less than 0.001 is, you guessed it, there's case number 76. We do have other cases with small p-values, but 76 is clearly the one that would be statistically significant at the 0.001 level. I do want to mention too that it's also possible if you want to perform a Bonferroni adjustment, utilize an adjusted p-value, you can certainly do so. But at any rate, I'm just sticking with the threshold that's given by Tabachnik and Fidel in their book. All right, so one other possible approach when it comes to looking at the squared Mahalanobis distances for potential high leverage cases is to create a QQ plot where we plot the Mahalanobis distance squared against expected values in the chi-square distribution. So we can do that if we go up to Analyze, Descriptive Statistics, go to QQ plots, and I'll move Mahalanobis distance index over, and then under test distribution I'll click on chi-square. Where it says degrees of freedom, we include 2 for the degrees of freedom from our regression model. So just keep in mind that when we are performing that significance test, or when we're creating a plot such as this, the degrees of freedom is referencing the number of predictors in your model. It's not, we're not incorporating the dependent variable as another in that computation or anything of that nature. So we're only referencing the number of predictors. So now I'll click on OK, and so now when I look at this, you can see in this plot right here, the QQ plot, there's one observation that is clearly more discrepant from all the other ones. And so if I double click on this, I can actually use the Elements tab right here, go under Data Label Mode, and click on this. Now it says 100, and the reason why is because I've sorted on the Mahalanobis distance values that were in that column. So that's why it shows up as basically row 100.
So if I go back in here, you can see that in the last row of the data, it's associated with case number 76. If I wanted just to do this and have the case number show up or the identifier show up, I could easily do that. I could just sort on ID right here and kind of get it back to where it was originally. And then if I go back under Analyze, Descriptives, and QQ plots, and we'll just do this again. If I click on OK, then in this particular case, when I go to my QQ plot and double click, go under Elements and Data Label Mode, you can see that now it's associated with, there's our case number 76. Alright, so that pretty well concludes this video demonstration. Again, I encourage you to download a copy of the PowerPoint, and this video was associated with example 3, but there's a lot of hopefully useful information in there that you might find helpful to you on this topic. So thanks again for watching.